Hello, everyone. I hope you're all keeping warm and safe during this winter storm. Welcome to Lecture 6 in our course ECE 560. Before we get started, if you have questions, just let me know. Okay, so I'm going to quickly write down a quick review of what we have seen and also kind of background material for our topic today, which will be state feedback control design. So we have seen several things up till now, but with the objective of designing controllers in mind. So the first thing that we would need for this is the idea of controllability, and we have discussed this in detail. But just a quick review. So for a system, x dot equals ax plus bu, and y equals cx, right? Plus du, basically the controllability matrix. Can be formulated in a special way. So let's say if this is the controllability matrix, which is a function of A and B, it can be written as an augmented matrix of the matrix B and then A times B, then A squared B, all the way until A to the power n minus 1B. Okay, and B could be any dimension. Like if you have more than one input, then the matrix B would have more than one columns. So we said that the system is controllable if the controllability matrix CAB has full rank, right? So if this controllability matrix has full rank, then it is controllable or completely controllable, in other words. So in the previous lectures, we have seen cases where systems are not completely controllable, so you could always get a decomposition of a controllable subsystem. So if a system is controllable, basically you can design a state feedback controller. Controllable, then a state feedback controller can be designed. And last time we also saw various objectives that the state feedback controller can achieve. One example is to track a reference state. The other could be to make the system stable, or to meet design specifications. So several goals in mind when you try to design a controller. So after the controllability test, we saw something called the controllable or controller canonical form. Okay. So what is a controllable or controller canonical form? It is a special form of the matrices A and B that makes the system be in a canonical form. So a system is in controller canonical form if basically the matrix A has a special structure wherein you will have 0, 1, 0, and then all zeros. And then you have like an identity matrix after the first column. So this goes all the way where you will have zeros here, and then 0 and a 1. So there's an identity in this box here. And the last row is basically all the coefficients of the, so there's some coefficients here. Which are important. And the B matrix is essentially all zeros except the last entry, which is 1. And we've seen in the previous lectures how to convert a state space representation into this form. So let me write this down. Basically, these are coefficients of the characteristic polynomial. And in reverse order with a negative sign, right? Okay, so this was the controller canonical form that we have studied. And just a anecdote here that a system which is in controller canonical form is always controllable. Is always controllable. So in other words, only a controllable system can be converted into a controller canonical form. Okay, so we have seen all these things earlier. Now, with this lecture, we have primarily one goal in mind, which is to assign arbitrary closed loop poles of a controllable system. Right, so if you have an open loop system, it has a fixed location of poles, which are defined by the eigenvalues of the matrix A. Now, once you decide to close the loop using a feedback, then your goal is to essentially try to change the location of those poles into a new location that has some desirable properties. Okay, so x dot is ax plus bu. This is the open loop system, and your feedback controller would be a state feedback controller, meaning you try to feedback the state information. So your u will be minus k times x, meaning it's a combination of the different states of the system. Right, so you have the system which takes input u, and there is a x dot equals to ax plus bu dynamics going on. There's y equals to cx, so your output here is only y. And remember the poles of the system are actually the eigenvalues of the matrix A. So eigenvalues of A are the open loop poles. Right, and once you implement the feedback controller, the new poles of the system are called closed loop poles. Okay, so this is the goal that we have in mind, and our claim is that if the system is controllable, then we can basically assign arbitrarily. We can place the poles arbitrarily using if state feedback, right? So then we can assign arbitrary closed loop poles by means of a state feedback. Okay, excellent. So for feedback law. So let's write the term law here. So that law is actually means that u is equals to negative kx, and which in other words means there's a vector of gains. So there's k1, k2, all the way to kn, and that gets multiplied with the vector of states, which are x1, x2, all the way to xn. Right, so if you multiply them, you will get minus k1 x1 plus k2 x2 all the way to kn xn. Right, so the u is actually minus the sum of i1 to n ki xi. Right, so this sort of feedback is also called a linear state feedback. Right, so we started off with a linear system, and the reason is because it's simple to analyze and work with. And now when it comes to designing a feedback controller, again, we use a linear state feedback, again, which is compatible with the type of system we are dealing with. So today's topic, as you've kind of figured this out in this introduction, is to do pole placement. Right, so we want to place the poles of the system. Oops. Via state feedback. So that's the broad goal of the system, of the lecture today. So in other words, if you want to understand what we want to do, we are looking at the traditional system, right, which is the standard LTI system. We have a fixed location of poles, and from here we want to go to a feedback system, right? So we are transitioning from this open loop to this new system where we have feedback. So, but remember, the problem with feedback is you do not have the state information, right? So the dynamical equation x dot is ax plus bu, does not give you what is the state at any particular time. So as I mentioned last lecture, that state has to be estimated from the output and input information. So there is always an observer sitting somewhere. Observer role is to basically give you an estimate of what the system state is at a certain time. So in other words, you will have x hat, which is the output of the observer, and hopefully if the observer is nicely designed, then the x and x hat are very close. So let's say you have that state information, then you can multiply it with the gain matrix or gain vector and eventually use it as a negative feedback, right? So there's a negative sign here, and this aggregator will have also a reference signal coming in. And the reference signal can also, most cases, it can be 0 because you can always assume that there's a shift in your state, right? So if you change your initial condition or you change your notation, then you can always assume that the reference is 0. Okay. So in other words, I mean, if there is a R that the X has to go to, then I mean, you can assume an X star or X2 is R minus X, the original X. So then if X goes to R, then X2 goes to 0, right? So the reference for X2 is 0. So that's the nice thing about this feedback design. Okay, so I mean, when we go from this open loop system to the closed loop system, there's something happening in the background. So let's look at the pole 0 diagram. So imagine that this is the real imaginary plane that describes the poles and zeros of the open loop system. So consider that it has 3 poles. So these are the poles of this open loop system. Now, once you have a feedback loop, your goal will be, for example, if you want to do if you want to make the system stable, you would want these unwanted poles to, or the poles in the right half plane to go into the left half. So maybe you would want them to go here. Right, so this is just an example that with the feedback, you can push these poles here. So overall, the feedback or the closed loop system will be stable. Okay, so this is pole placement. Via state feedback. Okay, so so let's look at the mathematical description of the feedback system. So the feedback system, by looking at this diagram here, can be expressed as follows. So there's this original dynamics, x dot equals to ax plus bu, but in the feedback diagram that U is basically R minus KX, right? So so one thing here, just to make things simple, I mean let's not look at the observer story here. So let's just assume Y equals to X, right? So I mean that's one possibility where your output is just the state. So in that case, you can directly use it as the feedback. Right? So it's just to make things simple and not to involve the X hat right now. But in the next lecture, we will start to eliminate this assumption and start to work with the X hat. So here, I mean, if you just assume that the output has all the state information, this U is basically R minus KX. Right? Looking at the diagram. So if that's the case, then this dynamics can be written as AX plus B times R minus KX. Okay, so in other words, X dot is AX plus BR minus BKX. Okay, which can further be written as X dot is A minus BK X plus BR. So this is the kind of new dynamics after feedback. So let me just mention it here. These are the new system dynamics after linear state feedback. Okay, so if these are the dynamics, then so we want to make sure that the poles of this system, which is our new closed loop system, are in a at a certain location. So what are the poles? So as we know, basically the poles are the eigenvalues of.
Sorry, Professor.
Yes.
This R shouldn't be zero now. You said we assume that it is zero, but now in the equation we have it.
No. I'm just trying to say that you can always assume it to be zero because you can always find an equivalent system where R is zero. But in general, there is R somewhere. So I mean, I'm just trying to say, if you don't want to consider R, that's still okay. But generally, you are trying to track a reference.
Okay, thank you.
Yeah, I mean, I'm not sure if I'm clear. My point was that if there is a system with R, right? And let's say there's a K here. And there's X dot is AX plus BU. So you can always convert it into a new system where you change the state, right? You assume X equals to X2, let's call it or X star is R minus X.
Yes.
Right.
Okay.
So you will have X star dot is some A star X star plus B star U, which you can directly, I mean, there's no need for R now. Do you get the point?
Yes, thank you.
Yeah, I mean, this R can go inside the X. So in general, you can always have R here, but it really doesn't matter. You see, the R is only playing a role here, but we don't care about this. What we care about is what is sitting next to the X. So the poles of the feedback system are actually the eigenvalues of A minus BK. All right, so if you want to assign the poles to any arbitrary location, we have to design K in a way that guarantees that the new poles are in the place that we want them to be. So assigning the closed loop poles is equivalent to assigning the eigenvalues of A minus BK. Right, so if let's say there's a matrix A which has some A has some numbers, so it has some eigenvalues, and we want to design K such that the new matrix A minus BK, which obviously would have some different numbers here, the eigenvalues of this matrix are at the places that we want them to be. Right, so the question is, what K will make A minus BK such that its eigenvalues eigenvalues are at certain locations. Right, so it's like I'm asking you to design a matrix, right? So we have to see where all the entries of the matrices should be, which makes sure that eigenvalues of A minus BK are at certain locations. And again, you see, this is a hard problem. So that's where the beauty of controller canonical form comes into the picture. So I will write it down. So in solving this problem, the controller canonical form dramatically simplifies the issue. And you will see it in a minute. Comes into picture. So so let's go back again to the controller canonical form. So any A which is in canonical form will have this structure 0, 0, and then there that follows the pattern. And then there's a 0 and 1 here. And the last row is, if you recall, it is negative A0, negative A1, negative A2, negative AN minus 1, and negative A, oh, actually it's N minus 2 and N minus 1. And the vector B is all zeros, and the last entry is 1. Okay, so this is the original system in controller canonical form. Now let's look at what is the BK and A minus BK look like. So if you say B times K in controller canonical form, it will be, all zeros. The last element is 1, and the K is K1, K2, Kn. So, and this is N cross 1 times 1 cross N. So the result is going to be a N cross N matrix. So it's going to be, so you will have all the rows to be 0, except the last one. Right, so you will have 0, 0 everywhere. And the last one will be K1, K2, Kn minus 1, and then Kn. Okay, so and then now if you do A minus BK, so let's see how would that look like. So it will be again the standard form. Zero, zero, 1, 0, 0, and then 0, 1, and the last entry will be little interesting. It will be negative A0 plus K1. The second will be negative A1 plus K2, and then negative A2 plus K3, right? All the way where this one will be negative A n minus 1 plus Kn, right? And then this one will be negative A n minus 2 plus Kn minus 2, Kn minus 1. Okay, so this is the structure of A minus BK. So you see the complexity of the problem has reduced in the sense that now to make sure that the poles are at certain place, we only need to figure out the last row of this matrix. We don't have to know what is the value of every entry in the matrix A minus BK. Okay, so just a quick note that if A is in controller canonical form, then you have noticed that A minus BK is also in controller canonical form. right? So if A, B are then A minus BK is also in okay. Now, so if you look at the structure of this feedback, the matrix after feedback design, basically you will observe that the last row of the matrix consists of entries which are coming from the poles, right, or the coefficients of the characteristic polynomial. So let's write that down also as a new note, that your characteristic polynomial of the matrix, has two properties. Its roots are the poles, and also the coefficients are the coefficients basically form the last row in the controller canonical form. Right, so from the characteristic monomial, which is, let's say, a n minus 1 s to the power n plus so on, plus a1s plus a0, right? That's the characteristic polynomial. So a0, a1 basically form the last row of the controller canonical form, and s1, s2, those are the roots of the characteristic polynomial, and they are also the poles. So so the observation that we can make here is that when the system is in controller canonical form, then each control gain, which is the k, actually only affects one of the coefficients of the characteristic polynomial. Right, so k1 is affecting here, k2, k3, and so on. So when the system is in controller canonical form, then each control gain, which is ki, it actually small ki, affects only one of the coefficients of the characteristic polynomial. So, I mean, this makes the controller canonical form very convenient, right? So therefore, the controller canonical form is convenient for control design. So until last lecture, it might have seemed, useless to use a controller canonical form or all these different forms. It's hard to make sense out of them, but once you start getting into the control design, you will see that this form is very convenient if you want to do a linear state feedback, because doing a minus bk will only change the last row, and all you have to do is figure out what the last row should be so that your poles are in a certain place. So let's write down the generalized procedure for pole placement of controllable system. So I'm just going to quickly summarize this procedure before we get into some examples and see how it gets to work. So procedure for pole placement of controllable systems. So the first step will be, if you're given any system, first step should be to convert it into, so convert the system into controllable or controller canonical form. Okay, using maybe a similarity transformation or you can have multiple ways to do it, or using characteristic polynomial. Right, so remember, characteristic polynomial for a system is the same no matter which form it is. That's why we call it characteristic, because it's unique to a particular system. So I mean, if you convert the system into controller canonical form, it will have the same characteristic polynomial. So maybe a used or a convenient way to convert a system to a canonical form could be to use characteristic polynomial and use the coefficients to construct it directly. But whichever way you want to do it, the first step should be to convert the system into a canonical form. And then the next step will be you solve the pole placement problem. Or maybe let's write down in a better way. So for the second step should be to determine the desired characteristic polynomial. Okay, and then from there you solve the pole placement problem. Right, or in other words, you figure out the gain k, and lastly you can convert back to the original. So convert back to original coordinates. Coordinates to obtain the control input. Okay, so that's the general procedure, and I mean, we have to see an example before it becomes really clear. So let's write down a system. So we have a dynamical system x dot is ax plus bu, where the matrix A is -15, 8, -7, 1, and the vector B is 1, 1. Right, and the question is, or the objective is, find a state feedback law to place the closed loop poles of the system at S equals to -10 plus minus J. So, I mean, we are given that the desired poles should be -10 plus J and -10 minus J. There are two different poles that the system should have. I mean, currently the system has different poles. We don't know, but we'll figure it out. So first step is really to convert it into a canonical form, right? So at least we know what are the coefficients, and how can we change them in order to modify the poles. So convert the system to controller to the canonical form. Now, so one way is to, I mean, actually, the shortest way is using the characteristic polynomial. So let's say the characteristic polynomial of A is by definition the determinant of Si minus A, right? So, which is basically the determinant of the matrix S plus 15, -8, 7, S minus 1. So if you take the determinant, it will be S plus 15 times S minus 1 plus 56. So it turns out to be S squared plus 14S plus 41. Right, so that's our characteristic polynomial. So if you figured this out, then it's very easy to go to controller canonical form. All right, so then controller so it will be A bar. It's going to be 0 and a 1 here, and the last row is really the key, so that you can write it as -41 and a -14. And remember, this is the -A0, and this is the -A1. Right? If you think of if you think of the characteristic polynomial to be a2 s squared plus a1s plus a0, then if you compare with this, then your a0 is 41 and negative a0 is negative 41. So that's the first element here. And this is a1 with a negative sign. All right, and then the b is obvious. You don't even have to do anything. It is 0 and 1. So this is our canonical form per se, which we are going to use in the control design. Okay, so we've figured out the controllable form, and let's also figure out the transformation that results into this form, because if you want to if you want to go back to the original system, then that transformation will be helpful. So let's do it here. Or let's say similarity transformation for canonical form. So if you recall, we have to use the controllability matrix. So CAB, which was B and AB. So this was basically the vector B, which was 1, 1. And then A times B, which turns out to be -7 and -6. So so we need this. I mean, before that, I can actually write the transformation formula for you. So if you remember, the T matrix is actually controllability A bar B bar times controllability of AB inverse. So CAB we have figured out. Now let's look at the CAB A bar B bar. Again, it will be A B bar and A bar B bar. So it's also simple because B bar is 0 and 1. And if you multiply these two, then you get 1 and -14. Okay, so then T is simple. So T will be this matrix times the inverse of the second matrix. So that's going to be -1, 1, 8, -7. Okay. So, and you can actually check that, you can verify, this, that T inverse equals to A bar, and T times B equals to B bar. But anyway, I mean, that's not our goal here. That was a step 1. And the next step is, so we determine the desired characteristic polynomial. So our step 2 is desired characteristic Okay, so I mean, we are given that the desired poles are locations. The pole locations need to be -10 plus j and -10 minus j. Right. So if these are the pole locations, maybe let's write them more clearly here. So the pole locations should be -10, s equals to -10 plus j, and s equals to -10 minus j. Okay, so I mean, then therefore the characteristic polynomial is actually s plus 10 minus j times s plus 10 plus j. Right, so if you know the roots of the polynomial, then you can find the polynomial directly. So this will result in s squared plus 10s plus sj plus 10s plus 100 plus 10j minus sj minus 10j plus 1. So this, if you simplify, this goes away with this, and 10j goes away with this. So what you're left with is s squared plus 20s plus 101. Okay, so this is the desired characteristic polynomial. Now, by looking at this, again, it is very obvious where what the controller canonical form would be. So therefore, so the closed loop system matrix in controller canonical form should be a bar minus b bar k bar. It should be 0, 1, and minus 101 minus 20. Right, so this should be your a minus a bar minus b bar k bar, which are all in controller canonical form. So I can clearly see here that these are the coefficients of desired characteristic polynomial. Okay. Now, this is where we want to get to, and we want to see what the k would be. But we can only figure out k bar at this time. So that brings us to our next step, which is to solve the pole placement problem, right? Actually, I should say k bar here. So So the problem is, you know, that that A bar minus B bar, K bar should be in a particular form, right? So it is 0 and 1, but the last row, as we have seen, it will be negative negative A0 plus K1. So A0 bar, K1 bar, and the second one is minus A1 bar plus K2 bar. So that should be the form, right? So by comparison, but we see here that that A0 bar plus K1 bar is actually 101, right? So if you compare these two, this is what it is: A bar minus A0 bar plus K1 bar is 101, and then A1 bar plus K2 bar is 20. Right, so so what is A0 bar? We can actually go back into our original form, controller canonical form. This is the A0 bar sitting here, and A1 bar. So A0 bar, A0, actually I should say this is A0 bar because these are entries in the matrix A bar. And let's also say bar here. So, okay, it is 41. So this A0 is 41, and this number is 14. So so therefore, the feedback law, I mean, so if you have this, then you know you can actually compute K1 bar is equals to 101 minus 41, which is 60, and the K2 bar is actually 6, right? So the feedback law that you have law is actually U equals to minus K bar X bar, and it's actually minus 66 and X1 bar, X2 bar. Okay, so we have found the K, or K bar actually. So this is the K bar. Now, last step is to actually go back into the original coordinates, which is X, right? So because we were solving this in the canonical form, which makes it very easy, right? Canonical form, you just need to figure out the last row, or only K1, K2, that's it. The rest of the matrix you don't really care about. So canonical form has this beautiful property, but end of the day, you know, you have to go back to original system. Oh, and this is step 4 here. Convert to original coordinate system, right? So what does that mean? That means, you have to go from minus k bar x bar to x, basically. So in other words, this means that because x bar is tx, so you will get minus k bar tx. Right, so from here you can say that this is your k. So let's do it here. I mean, this u is actually minus k bar was 60 and 6, and your t transformation matrix is, I mean, if you go back and see here, it is minus 1, 1, 8, minus 7. So we will just use that here directly, and that's going to give you your gain vector k. So it's minus 12, 18. Okay, so what you can say here is that the full state feedback controller is u is minus, or u is 12 x1 minus 18 x2. So that is your final result, right? And you can verify that if you use this u, then the resulting poles of the system are going to be at minus 10 plus minus j. So you have achieved your objective. So that's the whole process of converting one system to another system such that its poles are arbitrarily placed wherever you want, using a state feedback law, which is linear function of the state. So here's the full picture. So if you're able to have the state information of the system, you can simply combine it linearly using a gain matrix k and feed it back to the input. And the numbers k can be made such that the poles of the new system are whatever you want. So in our case, we said the poles should be here. Let's say this is minus 10 plus j, and this is minus 10 minus j. So the process has given you a gain vector k, which will result in this shift. Okay, so this process has another simpler formula. So that's called Ackermann's formula. So this is another way of doing the same thing. So it's important that we mention it here before we move on to other topics, because it's essentially a concise way of doing it. So Ackermann's formula for pole placement. So instead of doing all the steps that we did, there's a shorter way, which says the linear state feedback controller for a system x dot is ax plus bu, where U is minus kx can be obtained as follows. Right, so the formula is that K equals Q1 alpha C of A. Right, so what is the Q1? Q1 is the Q1 is the last row, of the controllability matrix inverse. A n minus 1 B, and there's an inverse here. So I mean, all these are, these formulas are good for computers to do because, you can always give them a algorithm, and then that helps compute things efficiently. The previous process that we did is more of a manual way to do it, but if you're doing it with more computational power, then there are formulas that can directly do it. And it's been implemented in MATLAB already using the functions for state or for pole placement. Now this alpha C is the desired characteristic polynomial. So desired characteristic polynomial with S equals to A. Right, so alpha C is a polynomial and it's a function of A, meaning that instead of saying this, you can say evaluated at S equals to A. Okay, so we can actually do an example to see how this actually works. So let's do a second example. So let's say x dot is 1, 1, minus 1, minus 2, x plus 2, 1, u. Then the question is to place the closed loop poles at minus 1, minus 2. Right, so that's the goal of the problem. You can always go to the previous route, using that controller canonical form and then transforming this. But this Ackermann's formula, let's try doing this. So let's say the Ackermann's formula, the first thing is the controllability matrix, right? So the CAB is going to be BAB, which in this case is 2, 1, and 1, 0. Right, so therefore the CAB inverse is going to be the inverse of this controllability matrix, and it turns out to be 0, 1, 1, minus 2. Okay, so this says So the Q1 in Ackermann formula is actually 1 minus 2. It's the last row of this thing here. And the desired characteristic polynomial is coming from the desired poles. So because the poles are at -1 and -2, so this will be s plus 1, s plus 2, which is essentially s squared plus 3s plus 2. Right, so this is alpha c of s. So now,
Professor, can you explain why you inverted CAB again?
okay, so I'm looking at the Ackermann formula, right?
Yes.
Ackermann formula is this. So where Q1 is a row vector, which is the last row of this this thing inverse, right? So the inverse is in the formula.
Oh, okay, I see, I see.
So the last row of this inverse turns up to be, you know, this thing here. Okay, now the alpha c part. Alpha c is like the desired characteristic polynomial, and we have to substitute the matrix A in it. So characteristic polynomial turns up to be s squared plus 3s plus 2. So to do the alpha c of A, we have to do a squared plus 3a plus 2. I mean, you cannot do 2 because it's a number and you're doing a matrix operation, so you have to put I here. It's an identity. To because of matrix function. So so a squared will be a times a. So it's 1 minus 1, 1 minus 2. Times the same thing. Three minus 3, 3 minus 6, and then this matrix. So it turns out to be 5 minus 2 and 2 minus 1. So now let's use the Ackermann's formula. So now basically your K is a Q1 times alpha C of A, right? So this is Q1 is 1 minus 2, and then the alpha C, which is 5 minus 2, 2 minus 1. So it turns out to be 1, 0. Right, so this is the K directly. So finally, you know, the state feedback law should be U equals to minus KX equals to minus 1, 0, x, right? So it's equals to minus x, 1. Okay, so, that's the Ackermann's formula with which you can also find the gain k directly. So just to make sure this is exactly the gain which would be found otherwise, we can also do the second approach, and let's call that the generalized approach. By the generalized procedure. So the generalized procedure, we have to do step 1, right, which is canonical form. So the characteristic polynomial of A is the first thing to do. That is the determinant of Si minus A, which if you do Si minus A, it will be S minus 1, 1, minus 1, and S plus 2. And if you simplify this, it turns out to be S squared plus S minus 1. Okay, so that if that's the determinant, then the controller canonical form can be written directly. So the controller canonical form is A bar equals 0, 1, and B bar is 0, 1. So now the coefficients of the characteristic polynomial, I mean, this is A0, and this is this is A1. Okay, so we have to do minus A0, so it turns out to be 1 here and a minus 1 here, right? So the minus A0, and this is minus A1. So that's good. Now, so step 2 will be the similarity transformation. So let's quickly find that out. So it starts with the CAB, right? So the T is CA bar B bar times the CAB inverse. Okay, so CA bar B bar, you can see directly from here, it's going to be 0, 1, 1, minus 1. And we've already figured out what the CAB is before. I'm just going to reuse that. Okay, so then T is actually 0, 1, 1, minus 1 times the, oh, actually this is the incorrect one. So what is CAB? So CAB is 2110. And the CAB inverse yeah, CAB is 2110, right? So here we have to use the inverse. So eventually this, if you do it, this goes to be 1 minus 2 and a minus 1, 3. So that's the transformation. And the next step is to solve the pole placement problem in the canonical form. So pole placement in canonical form, that starts with the desired characteristic polynomial. So desired polynomial is s squared plus 3s plus 2, because the poles are at 1 and minus 1 and minus 2. So this is direct. So we know, we know that the a bar minus b bar k bar, which is the canonical form version, should be 0, 1, minus 2, minus 3. Right, so this thing here is actually minus a0 plus k1 bar, and this thing here is minus a1 bar plus k2 bar. Okay, so if you know this, then comparison can help you find out the k1 bar and k2 bar. So comparison says a0 bar plus k1 bar is minus 2, and a1 bar plus k2 bar is I mean, actually we can drop the signs here. It's 2 and 3. So from here, I mean, this a0 bar, you know from earlier. I mean, this is coming from, my God, again, I should have written a0 bar here. So a0 bar is minus 1 and the other is 1. So knowing this, k1 bar is 3 and k2 bar is 2. All right, so now you've got the controller. So your u is minus k bar x bar, and it's minus 3 to x bar. And now the final step to get back to original coordinates. You saw that that is not a problem. So your u is minus k bar x bar, but is actually is a tx, right? So x bar is tx. So that makes it simple because it's simply k bar tx. So minus 3, 2, and then the transformation t, which was 1 minus 2 minus 1, 3, and x at the end. So if you simplify this, this turns out to be minus 1, 0, x, right? So therefore, u is minus x1, right? So verified. So you can see so the generalized procedure also goes to the same results in the same controller, in the same gain K as Ackermann's formula. Okay. I mean, we can do a another larger example to give you more insight into or more practice into the process of designing a feedback controller in the time that is remaining, so that we avoid starting new topics. So let's do another example. Hopefully that makes it clear for everybody. So X dot, it's a larger system now, -5, 1, 0, 0, -2, 1, and a 0, 0, -1. So this X plus 0, 0, 1 U, and the question is to place the poles at S equals to -4 and -1 plus -2J. Okay, so again, I'm going to do it using the two methods. The first one is by the Ackermann's formula. You will have some exercises in your homework 3 that is going to be uploaded tonight. So hopefully that gives you more practice into it, and then you're more comfortable doing state feedback control design using or doing pole placement via state feedback controllers. Okay, so remember, for Ackermann's formula, basically your K is the Q1 times alpha C of A, right? And basically Q1 is the last row of CAB inverse. So I'm going to directly start with the controllability matrix CAB. In this case, it should be B and AB and then A squared B, because we have 3 states here. So the vector B is 0, 0, 1, and A times B is actually the first row. It's actually the third column. So so if you multiply this, you will get the third column here, and that becomes a row. So you'll have 0, 1, and -1. And if you do it again, basically you're subtracting the 2 columns. So 1 minus 0 is 1 here, and then -2 plus 1 is -1, and then a 1 here. Okay, so next thing is to invert it. So CAB inverse is, I mean, obviously you can compute it later, but I'm going to write it down here directly. 2, 1, 1, 3, 1, 0, and 1, 0, 0. So looking at this, basically, this is your Q1, right? So it's the last row. So Q1 is 1, 0, 0. And the alpha C is the desired characteristic polynomial. So let's quickly figure out the desired characteristic polynomial, which is alpha C of S. It's going to be based on where the poles should be. So poles should be here. So we do S plus 4 and then S, and then S plus 1 minus 2J, and the conjugate part, which is S minus or S plus 1 plus 2J. So if you do this, so let's say S plus 4 stays here, you get S squared plus S plus 2J, 2J S plus S plus 1 plus 2J minus 2JS minus 2J plus 4. So we'll see some cancellation here. I mean, this goes with this, 2J goes with 2J. So we are left with S plus 4 times S squared plus 2S plus 5. So it turns out to be S cubed plus 2S squared plus 5S plus 4S squared plus 8S plus 20. And essentially it is S cubed plus 6S squared plus 13S plus 20. So the Ackermann's formula says K is Q1 times alpha CA. So the polynomial has to be operated on the matrix A. So remember, the Q1 will be 1, 0, 0. Let's see if that's the, yeah, that's Q1. And they multiply it with A cubed plus 6 A squared plus 13A plus 20I. So remember, this I is very important here, right? If you don't do I, then you cannot add the matrices. All right, so I mean, I'm not going to compute it here. Obviously, this is more convenient for computers to do. A cubed plus 6A squared plus 13A. But I'm just going to write the result here for reference. So this turns out to be minus 20, 10, minus 2, 0, 10, 2, and 0, 0, 12. Okay, so K, if you evaluate this, it turns out to be minus 20, 10, and minus 2. So the feedback control law is the U equals minus KX, and which eventually says it is, 20x1 minus 10x2 plus 2x3. Okay, so that's the first first type of method that can be used to do this. Okay, now second generalized procedure. So these examples are actually good reference for you to solve the homework, and I hope everybody understands what is going on here. The idea is very simple. You want to make sure that the eigenvalues of the feedback system are placed in a place that you want, but there's a caveat here. I mean, right now what we are doing is a very idealistic scenario where the state is available to you, like you have access to the X at all times, which is only possible if output Y equals to X. Otherwise, the state is hidden inside. You cannot figure that out. And you may argue that why don't we solve the dynamics X using, remember we did a solution to the state using initial conditions and so on, and transition matrices. Now the problem with that is there is an integral in that expression, and that integral is from 0 to a particular time, capital T. So if you want to figure out the state at every time, you have to keep computing that iteratively, not iteratively, but continuously. So that's where the complexity is. So this is not a practical solution. So the better way is to use observers. Observers are kind of estimators that give you an estimated value of the state at each time, and we will see in the coming lectures what an observer is, how do we design observers, and how can they be accurate and stable, and so on. So that's a more a richer controller than this one. Right now, what we have is a static feedback, which is just constant gain times the state. Right, so this is a simplistic, the most simple controller that you can design. But obviously, if you start to complicate things more, then the controller will also be more and more complicated. So let's go back to the generalized procedure, where the first step was to convert to canonical form. So canonical form, we start off with characteristic polynomial. Which is determinant of Si minus A, which is equivalent to the determinant of S plus 5 minus 1, 0, 0, S plus 2, minus 1, 0, 0, S plus 1. So if you have this, then this turns out to be S cubed plus 8S squared plus 17S plus 10. So the controller canonical form can be obtained as, so I need volunteers here. Can somebody help me write the controller canonical form? So I mean, I want the A bar and the B bar. Can-
0, 0, 1, 0,
This is the row or column?
row,
So 0, 1, 0.
0, 0, 1,
Okay.
minus 10, minus 17, minus 8.
Okay, perfect. And what's the B bar?
0, 0, 1.
Yeah, perfect. So it's a standard B, and the last row is the most important. This is basically minus A0, bar, right? This is minus A1 bar, and this thing here is a minus A2 bar. So step one is okay. The next step is the similarity transformation. How did we get here? So similarity transformation had the formula T, which is C of A bar B bar times CAB inverse. So the A bar B bar can be written easily as 0, 0, 1, and then 0, 1 minus 8, and the last one is 0, minus 8, 47. Then the CAB, let's see, we have, I think we have computed it earlier, so it's here. And actually CAB inverse is also there. So let's make use of this. So it's 2, 1, 1, 3, 1, 0, and 1, 0, 0. Okay, so if we multiply this, then we get our T to be 1, 0, 0, minus 5, 1, 0, 25, minus 7, and 1. And after this is our next step. So step 3 will be to solve the pole placement. So for the pole placement problem, basically we start off with the desired characteristic polynomial. I mean, we have already computed it in the previous method, so I'm just going to say it is s cubed plus 6s squared plus 13s plus 20. So then our A bar minus B bar K bar, which is the canonical word, we are in this shape. So 0, 0, 1, we have minus 20 here, we have minus 13, we have minus 6 here. Right, so in other words, this basically is minus A0 bar plus K1 bar. And this here is minus A2 bar plus K3 bar. Okay, and then the next step is comparison. So by comparison, basically A0 bar plus K1 bar is 20, and then A1 bar plus K2 bar is 13. This should be 6. So, I mean, this value here is, let's go back and see the bar is actually 10, 10, 17, and 8. So this is 10. This is 17. This is 8. So essentially, our K1 bar is 10. K2 bar is -4. And K3 bar is -2. The last step now is to convert step 4, convert to original coordinate system. So the U is minus K bar X bar. So we will say this K bar TX, right? So it's a 10 -4 -2 times the T, and T is 100 -5 10 25 -7 and 1. So remember, that's the similarity transformation matrix T and X here. So if you multiply this, you are going to get -20 here, 10 here, and -2x. Right, so which is equivalent to saying 20x1 plus or minus 10x2 plus 2x3. So you can check you can verify that both methods will result in the same feedback controller. And more examples will be in homeworks and quizzes. So, I mean, hopefully once you solve them, you will have a better idea of how to do it. I mean, maybe looking at it, it looks complicated, but it's actually very simple. And hopefully once you start doing it, then, you know, you get the hang of it. And try to do good practice of this, because this is going to be the basic step, and it's going to be used a lot in at least the next couple of lectures. So, you know, mastering this technique is important. So that's pretty much the end of our the technical content here. I'm just going to quickly write down a summary, you know, kind of giving you an overall picture. So, you know, the state feedback, as we've said, can be used to arbitrarily place poles of controllable systems. So that's important. If the system is controllable, which we know how to figure that out, then, you know, a state feedback, right? Remember that the idea is state, it's not output feedback. I mean, some people, you know, simplified diagrams, people think if this is the system, this is Y, this is, you know, the reference, then if this is the K, you know, people may tend to believe this this U is R minus KY, right? This is incorrect, because that's not what we are trying to do here, because the output y is a is not the right ingredient that we need to modify the state, because we have to eventually go to a minus bk, right, which is only possible if the k turns up with x, right? So right, so remember, sometimes people omit this, so you have to remember that there's always a x hat somewhere, or if you have this, then assumption is y equals to x, right? Which means perfect state observability, right? So it's perfect state information. So the full state feedback controller or maybe let's call this full state. So full state feedback controller is not implementable because state information is not or let's call it may not be available at the output. And then basically the next step is the observer design. So observer design is a way to estimate the state from the output and the input. So in other words, you want to say that your system is actually some reference going to the system, and generally you have y here, but you have an observer which gives you an estimate x hat, and that you can use as a feedback in with a certain gain. Okay, and so another observation in today's topic is that the pole placement procedure is it's only applicable to controllable systems. Okay, so if the system is not controllable, then we can decompose the system into controllable and uncontrollable part. Parts and use pole placement for the controllable subsystem. Right. I mean, hopefully it's clear to everybody that, you know, there's a, you know, system here, then there's a system here which has the U, right? So U is here, but U does not affect this part. So we have X controllable dot is some A controllable X controllable plus B controllable U, right? But there is also a X uncontrollable, and there's no U there, right? So it's only this part. Oops. So, I mean, there still can be an output depending on these two parts, and basically what you can do is to design a K here, which can be fed back. Right, so hopefully if the uncontrollable subsystem is stable, then, you know, you can play around with the controllable part only for various reasons, as we've earlier talked about. Another summary item is the fact that, I hope people appreciate this, that controllable canonical forms really makes it very, very convenient to design the controller gain K or K bar by shifting coefficients of the characteristic polynomial. Right, so only the A0, A1, and A2, and so on are shifted by K1, K2, and so on. So, I mean, this additive shift can be reversed to actually design your controller gain K bar, and that can be also inverted to go back to the original state space representation to get K. And lastly, we've seen Ackermann's formula.
Sorry, Professor, for canonical form, we obtain them from transfer function. If we have a zero pole cancellation at left half plane, again, we can use those transfer function. As far as I know, in the first lectures, you told us that it's not true to obtain the steady space from transfer function, but for those canonical form, we always do this. So if we have a zero pole cancellation, but in the left half plane, is it true?
Okay, so so as I told you, we are working with a characteristic polynomial, which is kind of the reason why we call it characteristic polynomial is because it captures the behavior of the system, right? And it's characteristic to a particular system. Now, in a transfer function, you may have pole zero cancellations, but that does not change the characteristic polynomial. I mean, I give you an example. So let's say your transfer function g of s is s plus 1, s plus 2, right? Now, somebody just deleted the, let's say the one part of it. Let's say somebody just kicked it out and said the transfer function is s plus 2, right? Which is maybe minimal representation, but it does not capture the complete picture. However, the characteristic polynomial, the characteristic alpha c of s is still s plus 1, s plus 2, which is s squared plus 3s plus 2. And this basically is coming from the poles of the system, right? So this we get from, so poles go to this. So poles are -1 and -2. So from there we obtain this this characteristic polynomial. Now, characteristic polynomial is always complete. There is no cancellation in here, but the transfer function denominator may have been eliminated to get you a minimal system representation, and that may have hidden some instabilities or some information. So what I would say is we are always using characteristic polynomial instead of the transfer function. I mean, as a fact, the denominator of transfer function is the characteristic polynomial, but maybe a better definition will be the determinant of Si minus A.
Okay, thank you.
Okay. Because determinant, you will not have any cancellations, right? It's already the denominator part. But if you do the Laplace the Laplace transform of Si minus A, I mean, if you do Si minus A inverse, right? So there's a matrix, and then and then you do the C. Sorry. This is the G of S, right? Now here you can have problems. I mean, once you compute this, maybe there's cancellation and denominator looks very bad, or may have some hidden information. But if you do this, then there's nothing that will be canceled, because this is already the denominator part. Okay, does everybody understand this?
Yes, thank you.
Okay. Anything else that people want to ask? Okay. So the last item was the Ackermann's formula, which is another alternative to find the feedback gain vector directly. And next lecture, we are going to start to talk about you know, the observer and how that changes our controller design. Right, in an ideal world, this is what you will do, that we have seen today. And I mean, this whole idea is great. I mean, if you want to make a system stable, you could do it by just designing a state feedback, and you determine the gain K, and that's going to make the system behave in a certain way. And you've seen, you know, how poles have a different role in the system behavior. If poles are here negative, then the system behavior is you know, oscillatory. If the poles are here only, then the system, has a smooth behavior. And if pole is here, the system decays faster. So, I mean, system behavior is largely controlled by the location of poles. And if you know the specifications of the system, like what is the desired response you have, you can actually simply design the gain controller K that steers your system towards something, some desired behavior. But remember, always, it's not as rosy as this. You will have constraints of power. You will have, obviously shifting a pole here from here may take a lot of energy, which may not be even possible. So there's always limitations and constraints that your gain controller may have. So but ideally, in an ideal world, this is what we could have done. But based on the specific system that you're dealing with, things can be very different. So essentially, I think this course will give you that background to apply this theory to a specific domain-specific applications. Obviously, the location of poles may have to do with system parameters like the mass or other, system parameters, and putting them into a particular location may mean something. So imagine that's the whole reason we just give you the locations of poles instead of you figuring out what to do. But in an ideal world, you could place anywhere the poles of the closed loop feedback system. So I hope you you understand the idea behind this theory, and you appreciate the value that it can create in a control systems. And obviously, in the next lectures, we're going to study more advanced forms of controllers, including dynamic. Right now, it is just a static controller, but we will also see dynamic controllers. Okay. Any questions before we close the session? Okay. If not, you're always free to send me an email, and I hope to see you next week.
Thank you, Professor.
Okay. Have a
Thank
great
you,
evening.
Professor.
Thank you.
Bye-bye.